Hello viewers, welcome to another episode of Space Science with Python. Last time we talked about the Sun and the center of our solar system, and we found out that the Sun is not 100% the center of our solar system, but the Solar System Barycentre. And well, every object in our solar system has its own gravitational pull, so all planets, asteroids and so on, and also the Sun itself. And this leads to a, let's say, gravitational center that it's not corresponding to the center of our Sun, but more like an object or a point in space that even is outside the Sun. So even the Sun revolves sometimes around or is wobbling around this point. And today we would like to see what are the main drivers of the movement of the solar system barycentre. Now, some of you may already say, yeah, come on, it's probably the larger planets, it's maybe the Earth, it's Jupiter, it's Saturn, and so on. Yeah, and today I would like to show you how to maybe determine or see whether this is true or not. And don't worry, we will not really dive deep into some theory, but we will really, do it more from a, I would say from a visualization perspective. So we visualize some parameters and interpret the results. Now, I created a new folder in my repository. The link is, as always, in the description. And I recycled some code from last time. So like, for example, the initial time, the year 2000, we compute the movement of the solar system barycentre for 10,000 days. I load some kernels, I create some time interval array that has the ephemeris time from the initial date to the end date with a step size of 1 day, so for up to 10,000 days. And we also use this time a new package. We use pandas as well. So I added it here in the requirements txt. So please do not forget to rebuild your remote container for this. Now we have this cell here with initial time and end time, and also we are loading again the radius of the Sun. Now, what is the goal, or what do we want to achieve today? We will compute the so-called phase angle between some objects in space. And what's the phase angle? Now take care, my extreme nice drawing skills will be shown now. We have here, for example, our Sun, right? Here's the Sun. And we have also some planets, but they're not square, they're, let's say circular, like for example, let's take another color for, I don't know, maybe let's take this color here and let's say this is Jupiter. So we have the Sun, we have Jupiter, and we have also the solar system barycentre. And for this, let's take the square shape. So this is the solar system barycentre, so that we know what we're talking about. So this is the solar system barycentre. This here, let's say it's outside the Sun. Now the center of the Sun, let's assume that we assumed in the beginning that the center of the Sun is not the center of the solar system, but of course, due to the gravitational contributions of Jupiter and the other planets, this is not the case. We have the solar system barycentre. So what we will do today, we will compute a vector from the center of the Sun to the solar system barycentre, and also from the center of the Sun to Jupiter. And this angle here in between, we will call this phase angle. And this word phase angle will also, we will continuously use it for other use cases also when we talk about asteroids later. And now you think, well, why might this interesting? Well, let's assume that, let's remove maybe all the planets. Then we would assume that the solar system barycentre is in the center, but Jupiter has a gravitational pull, so it moves the solar system barycentre outside of the center of the Sun. And maybe it's not really on the straight line, but maybe close to it, because we have also other planets, like for example, also Saturn or other planets that have their own contributions, leading to to an angle between the solar system barycenter and the respective larger planets. So yeah, sounds a little bit shady maybe, but we will see later that this makes a little bit sense to get some visual insights of the movement of the solar system barycenter. So again, this is not about really, we will not apply now any gravitational theory. We will just take a look at the data. So we will just keep it quite simple for the beginning. So what do we want to do? We want to compute the position of the solar system barycenter and the position of some planets. We want to compute the phase angle, and we want to do it for each individual ephemeris time. And instead of putting everything in individual arrays, we will work today with pandas, and for this we will use a pandas data frame where we will add all results of the solar system in a solar system data frame. Now let's run maybe everything so that the cells are working perfect. And the first step is we are adding our ephemeris time. So we are allocating the ephemeris time and take the time interval et. And maybe let's print also the solar system df to see what happens. And there we see this is the ephemeris time, the first column. So let's keep this print command to see how our data frame is evolving. Now we will also add the UTC time to have some human readable text, because later for the plot we will also like to have a proper format or something. And for this we say that we take the ephemeris time again and we apply a command over all rows. We say ephemeris time apply, and we apply a lambda function. In this case it's spicypie dot et to date time. So of course we could also use the defined array in the beginning, but this is another function I would like to show you. Simply the conversion of the ephemeris time back to the et. And then let's take a look how this looks like. So we see here that it's we have also here the midnight times, right? We were making a delta of one day, so let's get rid of the time. So we say the date alone is enough, and then we get the UTC date. Now we exceed our column width here. I think I set it to 100, I guess. And let's move it to the next line to format it a little bit properly. Again, the repository is in the description, so you don't have to follow everything now. You can just recycle the code you find on GitHub. Now the next thing is also we would like to compute the position of the solar system barycenter with respect to the sun. So the solar system barycenter as seen from the sun. We will also add this in our pandas data frame. So we say, okay, allocate a new column. We call it position SSB with respect to the sun. So let's keep it in a, let's say, human readable format. And we will use the ephemeris time, of course, because that's the basis of our computation. And we say we apply function, apply lambda x. And what do we use? We use SPK GPS. So the function we used last time, it's a function that returns the position of our computation, so x, y, z values, not the velocity, and the light time. So we have also to take care that we use the first result, namely the position. So we know we don't need the light time, so let's assign only the very first value. and the target is 0, so the Solar System Barycentre. Ephemeris time is the variable of our lambda function because we go through the ephemeris times. Our reference frame is ecliptic J2000, and the observer is the sun. Yeah, let's take a look. This seems to be working. Position with respect to the sun, and we got some results. Perfect. Now, working in a Jupyter notebook is sometimes a little bit, yeah, it can lead to a lot of errors, right? So what I show you now is of course prepared and everything, but if you would like to work and be sure what you do, I would also recommend to really use only Python scripts in the long run, and also apply unit tests or work in a test-driven development setup. In some future video, I will also explain you how to work in a test-driven development setup, but for now, let's stick with the Jupyter notebook. Now we can also maybe format it here a little bit more, so to keep everything clean and tidy. Now you may also ask, okay, how should I format my code here? Should it be everything under one column? Should I move this maybe to another line? Well, here in a Jupyter notebook, again, it's maybe, let's say, personal preference or so. But if you work with Python or you create your own library, I highly recommend to create a proper CI/CD pipeline where you can apply libraries, Python libraries that check your code for consistency and so on. So then it's not like speculating, but really, some proper checkup. But again, Jupyter Notebook, let's stay with this one. And also let's scale our position vector. So let's normalize it. Maybe we will need it later, especially if you want to compute the angles. So let's call it position SSB with respect to the sun, and then we call it scaled. And then we know it's a little bit too long, so backslash. So nope, that's not this one, but this one. Solar system, blah blah blah. And then we take this column here, and we apply again a lambda function, and this time it's the radius of the sun that we computed in our second notebook cell. Alrighty, and now we can also compute the distance. It's probably needed later also for the angle computation, but we will also see that it's not 100% sure true. But yeah, let's keep it like this. Let's recycle this line here. We call it as a position solar system barycentre is not the position, it's a solar system barycentre with respect to the sun, scaled, and then let's call it distance, because it's not a vector anymore, it's now a single float. And there we use the position, the scaled position, and apply again a function lambda x, and we can now use, of course, NumPy, linalg_norm, but also Spice has a functionality for this. It's simply called vnorm. So it's the same basically. So let's see, we have no errors. Compute the position with respect to the sun. What's this? Okay, it's not showing everything. We can click here. So the scaled position and also the distance, and we see here 1.6 sun radii, 0.93 sun radii, so changing values. Nice. This is the output, and we can keep this for now, I would say, in this cell here. So let's remove the print and keep it clean. Next cell. Well, what do we want to do? We want to compute the phase angle, right? And for what planets do we want to do it? Well, theoretically you can do it for all planets, but we want to plot it later, so we shouldn't exceed it too much. I just provide now here an NIF ID dictionary, and this dictionary, let's say, contains only 2 planets, or the barycenters of 2 planets. The first one is Jupiter, and the second one is Saturn. And of course, feel free to add more. Uranus, Neptune, they have then 7 and 8 respectively. You can also take Pluto, but I don't think Pluto has a huge impact. But also use maybe Mercury, Venus, and Earth. Feel free to extend the lesson of today. And what we do now is we would like to add the phase angle to our data frame. Now, instead of repeating the code twice, we can create a for loop where we iterate through this dictionary. Let's call it planet's name key f. Of course, we could also use other functions to separate between the keys and the values, but yeah, let's keep it simple. So first we could write planet column name. So let's define the column name. You can say it's an F string where we say let's write a position of the planet with respect to the sun. So for example, Jupiter, and later also Saturn. Also you can use Neptune, Earth, whatsoever. So position of the planet with respect to the sun. Now let's see whether this makes sense or not. Yeah. You see position Jupiter with respect to the sun is one column name we will add, and also Saturn with respect to the sun is another column name we will add. So this is quite nice. And another column name we will later add is also planet phase angle. So we call it like phase angle or angle column or column name. And there we do it like this same way. Phase angle sun, and then as seen from the sun, we take then the planet's name to Solar System Barycentre. So again, from the sun, the phase angle to the Solar System Barycentre, and from the between the Solar System Barycentre and the planet. So this is the second column name. Let's check if this also works. Yeah, this works as well. So there will be a column called phase angle sun, Jupiter to Solar System Barycentre, and Saturn to Solar System Barycentre. Good, we defined our planet names, column names, and now we can also assign a planet ID where we just planet's name key. So the ID that is required for spies to perform the computations. Now we can compute the position of the planet, and we can simply recycle this part here from our last cell. So let's add it here, and of course we have to replace this column name with our defined column name in our for loop. And of course, the target is not 0, but in our case, it's then the planet ID. Okay, and let's make it also here a bit more fancy. Perfect. So we will add a new column, which is, for example, called position Jupiter with respect to the sun. The planet ID is for Jupiter 5, for Saturn 6. So in a for loop, we create these 2 new columns. And then we can also now compute the phase angle. So now we have the position of the Solar System Barycentre as seen from the sun. And we will have the the distance between the sun and the planets. Yeah, so I'm confusing myself a little bit. But this vector is not normalized, but it really doesn't matter because, well, it's just the angle between two vectors. So the one is just scaled, the other one is not. So it really does not matter a lot. Last time I talked that we can use the dot product of two vectors to compute the angle. But thankfully, SPICE has also functionality to compute the angles between two vectors. But let's take a look first. Let's create the column. We will call it planet angle column. So this will probably also exceed our column width. We apply something for the entire data frame, so not for a particular column, but for the entire data frame, because we will need the position of the solar system barycenter as seen from the sun, and the position of the planet as seen from the sun. So we can use apply, and then we need to also define the axis. And no, I don't want to enable. So lambda x. And there is the function called SpicyPy vsep. So this is the function that allows us to compute the angle between the planet vector and the position of the solar system barycenter with respect to the sun. Yeah, we can use the scaled one or the non-scaled one. We have two separate columns for this, so this is fine. We can also just use this one here. But the result is provided in radians, so we have to convert it to degrees. Now numpy degrees. Close it here, and we have to take care of the axis. So that should be here. Axis equals 1. Now let's make this a little bit more readable, let's say. I know it's not the best solution here, but at least it's looking fine. You can also put the axis here back, so we separate the axis and lambda. Nice. Now let's see if this cell runs without an error. Yeah, and it looks fine. So we can just quickly print maybe the phase angle Sun Jupiter, for example, and we have some results, 14, 59, and some other values in between. Cool. So we will see whether this makes sense or not. We could also prove whether vsep makes sense or not. I will add later a cell where I compare vsep with the dot product. You can also do it by yourself. Try it out. A lambda function with two variables, and then you compute with the dot product the angle between two vectors. But again, I will add it into the Jupyter notebook in the repository. But feel free to do it on your own and test it out. Now we will create a graph. And what should the graph show us? So on the x-axis there is the time, so year 2000 until 2030 or 27 it was. And then we have one graph where we would like to see, for example, the distance between the sun and the solar system barycenter. So when is the solar system barycenter pulled away from the center of the sun? And then let's take maybe also the phase angle of Jupiter and Saturn to see, for example, if Jupiter and Saturn are in the same direction. So let's say they have a very small phase angle, then their combined gravitational pull is pulling the solar system barycenter away from the sun. So back to our small drawing. Let's assume, make this a little bit smaller. Let's assume this is Jupiter. Then, for example, our solar system barycenter is somewhere here. When later Saturn is maybe around here, let's say, it's just speculation, right? Our solar system is maybe here because their combined gravitational pull is pulling on the solar, or is moving the solar system barycenter maybe outside of the sun. We could also later add, for example, the other two gas giants, and maybe if they are in a line or closer, yeah, it doesn't have to be necessarily in one straight line, then the solar system barycenter is maybe here outside. Yeah, so let's take a look whether this makes sense or whether this happens or not. So what we will create subplots. We will create one with 2 axes. So if you would like to add the other planets or all 8 planets, feel free to do it. I think for today we just stay with Jupiter and Saturn. But as a small exercise, create a generic way to do it for all planets. I think this would be quite impressive. And if you like, please share your work also here or on Twitter. So we will create 2, cannot read, what? I didn't press something wrong. We will create 2 vertical cells. So in the horizontal direction is only 1. We will share the x-axis because yeah, we want to share the UTC, the date time. And the figure size, let's keep it simple or small, 8, 10 or something like that. Now again, as always, you already know me, we will use the dark background. Maybe move the dark background even here on top. Now we will move or iterate through both planets. Again, you can also do it a more generic way. I just want to write it down a little bit so that you you see what's going on. And again, I know it can be done easier or more simpler. So we will iterate through the axis. We use the planet abbreviations and we define some planet names. So we don't want to work with Jup and Set, but really with Jupiter and Saturn. We could have done it also before, but yeah, it doesn't really matter. So we will create, or we will iterate through x1 and x2. We will move through Jup and Set. That dot is wrong. And another array contains simply the words Jupiter and Saturn. Doing this, I'm wondering why I didn't do it before, why I call it Jupiter, Jup and Set. Maybe I just wanted to keep the columns short, but yeah, it doesn't matter now. Feel free to change the code to create a pull request if you think, hey, I did it better, my way is more generic, this is way too complicated and too much text. I fully agree, be my guest and help me improving my code. Now this is that. Now let's move into the and let's create a plot. So we could, first of all, we could create a title where the title says the name of the planet we are using. So we say set title, and the title is the planet name. And let's take a color, like for example, tab orange. It's quite nice. Let's see whether this works. Yeah, we have 2 plots. One is for Jupiter and one is for Saturn, but there is no content yet. So yeah, we need, of course, content. So let's add first the distance between the Sun and the Solar System Barycenter. So we will plot Solar System DF. We use UTC. This is our x-axis. And yep, here we will use now Solar System DF, and there we use the SSB with respect to the Sun scaled distance. So the suggestion of VS Code was correct. And as a color we use maybe tab cyan or something. Is it readable? I hope so. Yeah, this looks okay, I think. Yeah, this is okay. So you see here, yeah, here is the surface of the Sun, 1 sun radii. So sometimes it's going close to the center of the sun, sometimes the solar system barycenter leaves the sun. It's currently actually happening. So it's now year 2021. So yeah, it should be now outside the sun. The sun is currently at this very moment wobbling around the solar system barycenter. Quite impressive. Okay, so we should also create some X labels, I would also say, because otherwise it's not good or not well readable. So creating plots is also something like a little bit like art, right? I mean, if you write your thesis, for example, or if you write a paper, most comments are due to the plots. Yeah, improve this, improve that, remove this feature. It can be tedious, but it's sometimes also a little bit fun to improve the plots and see how your data is getting into life, let's say. So now we have the same color as the y axis label, but we would also like to set the ticks here also in the cyan color. So how can we do it with matplotlib? Well, this also works with the command tick params, and tick params allows us now to say, okay, for the axis y, we would like to change an attribute, namely the label color, and the label color is also tab cyan. So let's see. Yeah, it's also changing the color. So you can do it more. You can also maybe change the color of these small lines here, but yeah, let's not over-engineer the plotting here. We could also narrow it a little bit down. So to remove this empty space here and this empty space there. So we could say, okay, we would like to set some X limits and Y limits as well. So for this one, we take the minimum, or it would also be the very first entry of the UTC timestamp. Let's not get confused. And the maximum is basically the same, right? You could also use the first and the -1 entry. It doesn't really matter. So let's see. Datetime object is not callable. That's strange. Okay. Somehow I probably copy pasted it, right? So I did a mistake here. Now it works. And the empty gaps are missing now. So this is fine. And yeah, for the y limit, we could also say, I don't know, we could say like between 0 and 2, for example, right? I mean, so we see the core of the sun and the 2. We could also say 2.1 or so. Let's leave it with 2. I think this is very close to 2. Yeah. So just improving our plot a little bit. And now, of course, we need to add the phase angle, right? And for this, we need to create a twin. So let's call it like add, for example. And this one is our twin x. So the sharing now the x-axis. And now we add another plot here. In this case, it's the Solar System DF UTC. Auto-completion, please stop bothering me. Solar System DF. Again, in this case, it's again our F string because we are iterating in our loop. So it's the phase angle, phase angle sun, and then we used this abbreviation. Here it's called planet abbreviation. So in curly brackets 2 SSB, and we could, come on, daytime, leave me alone. And now we could use another color, like for example, tab orange. We use it as a title, so this makes also sense to use it. Tab : orange, and let's see how it looks like. Yeah, that's our plot here. All right. But first, let me click. Yeah, let me add also some coloring for this axis here as well before we take a look at the data. So xf add is now the y label, set y label, and the y label is like, I don't know, planet phase angle in degrees, and the color is also tab orange or orange. I need a comma. Yeah, this looks good. And then we can also use the tick parameters as well. So just add it here, orange, and it's also orange. Nice. That looks good. Perfect. Now another idea would also be, so what do we want to see? We want to see, let's go back to our plot, that, and let's remove this chaos here a little bit. So if we go back to our drawing with our vectors, we would like to see that the distance or the phase angle, a small phase angle corresponds with a larger distance. So if Jupiter is coming here, so the phase angle between the Solar System Barycentre and Jupiter, when it's small and the other planets are maybe also maybe like here, or let's say Jupiter is the main gravitational drive, that the Solar System Barycentre is moving out of the center, because, for example, the other planets are not bothering or having their own gravitational pull from the other side, moving the SSB like here. So we want to see something where a small phase angle corresponds to a larger distance between the center of the sun and the solar system barycentre. So this distance here, a larger distance, we would like to see a correspondence between larger distance and a small phase angle. So in this case, let's invert maybe our y-axis as well to see if we see some effects or not. No, not the x-axis, we want to invert the y-axis. And then also we set the definition range for all angles, so from 0 to 100 degrees, not 360, because, well, of course, the planet can move here, and then afterwards the phase angle is then smaller than 100 degrees. So the phase angle is only defined between 0 and 180 degrees. That's basically it. And now we can also, wait, I inverted it, right? So it should be 180 to 0. And then we can also add a grid so that it's a little bit more readable or so. We can use it here for the F1. And then we say, yeah, let's take only one for the y, for the y, so along the vertical lines for each year. So for the x, and then let's say, yeah, line style could be something like dashed, and we take also some alpha values, so it's not dominating the view. And then we can also create the label for the x-axis, which is then x2. And in this case, it's of course the UTC, so or the date in UTC. That doesn't really matter. It can also be called date or year. All right, let's make a tile layout. Come on. And basically this, we could also, let's take a look. reduce the distance between the two figures. Just for you to show how to do it, we just say subplots adjust, and there you can define the horizontal space. It's h space equals 2, and then you can set some number, let's say 0.2, and then rerun the graphs. We finished our graph now. Now, of course, you will say, whoa, I just developed here everything, blah, blah, blah. Of course not, right? I just worked on this prior to this video. So I just try to show you how I thought during the first time I developed it. Now it's more like reproducing these things and now also interpreting the data, which is also very important. And let's take a look. Again, we are not taking any theory or whatsoever. We just take a look at the graphs. Now let's have a look here. On the x-axis, we have now our date, 2000, 2004, and so on, until 2027, right? The cyan color indicates the distance between the solar system barycenter and the sun core in sun radii. So again, here at this time and also now, the solar system barycenter is outside the sun. On the right side, you see the phase angle, so the phase angle between the solar system barycenter and the planet as seen from the sun. In our case, we take a look at Jupiter and Saturn, but again, feel free to do it as well for all other planets to see the effects. Now let's see, what do we see here? For example, we see Jupiter, the phase angle moving here, between, okay, 40 degrees and 0. Here it's also 60 degrees. Here it's even once 0 degrees almost, but the solar system barycenter is like in the sun. So Jupiter has no huge gravitational pull to the solar system barycenter at this time. The solar system barycenter is in the middle, is in the center, or not in the center, but it's very close to the center of the sun, right, at 0.5 radii. Here now, around this time now, or 2022, the phase angle is again 0 degrees, and this time the solar system barycenter is way outside the sun at 2 sun radii. That's far away. So here the gravitational pull of Jupiter seems to have a way more severe effect. How is it that this time it's a huge effect and here prior it was no effect? Well, again, Jupiter is not the only player. We have a lot of players, for example, Saturn. And now you see here at the same time where we had not such a huge gravitational pull from Jupiter, we have a very large phase angle between the solar system barycenter and Saturn. It's almost 180 degrees. So what does it mean? That means that while Jupiter was pulling the solar system barycenter to the one direction, Saturn was on the other side, having its own gravitational pull, pulling the solar system barycenter towards its direction. And now a few years later, you see the phase angle decreases again. Why? Well, these planets are revolving around the sun, of course. So now it appears that Saturn and Jupiter are, let's say, at the same direction in space, pulling it together. So they are together pulling the solar system barycenter out of the sun. Now, of course, they are not the only players, but this is like a huge effect. So in our case, it could be something like, I know my drawing skills are awful. This is Jupiter, this is Saturn. Let's give Saturn another color. Red is reserved for Mars, right? I don't know, blue is for the Earth. Let's take green. That's fine, I think. So let's go back here. Here at this point, the solar system barycenter was somewhere here. Here was Jupiter. but at the same time, Saturn was on the other side. Take a look at the other planets. What was their effect, right? Now, a few years later, they are almost, let's say, in the same region, like here, for example, and together their gravitational pull is moving the solar system barycenter out of the sun. And this explains it, right? And without any theory, without any equations, complicated formula, just by thinking geometrically, we found out that, well, the main drivers are the two gas giants, Jupiter and Saturn. Of course, not the only ones. So feel free to extend this small, not analysis or graphs with the other planets. I hope it was not too confusing today. If you have any questions, feel free to ask in the comments, write me a DM or even on Twitter. All my social media channels are shared in the description. I hope that you enjoyed it. Next time we will move away from the Solar System Barycenter. We will cover another topic. I hope you're looking forward to it. I enjoy it. And yeah, stay interested with this, guys, and see you next time. Take care.